Good morning, everyone. Thank you all for coming for the early morning session after the concrete mixer. So my name is Weina. I'm assistant professor from Stevens Institute of Technology. And Dr. Consta just introduced the long title of my topic today. So the general background problem for this study is due to the fact that the climate change is impacting the Earth, and the temperature will continue increasing if we don't bring down the carbon emission. So concrete materials has a high CO2 emission because some of the raw materials are high carbon footprint, such as the cement. So the cement production is responsible for around 7% of the global CO2 emission. So there's many strategies that can decarbonize the concrete, such as use the lower carbon ingredients to replace, such as the solid wastes, to replace the binders or the aggregates, and also you can lower down the content of the energy intensive or the high carbon footprint materials, such as the fibers and some of chemical mixtures. So there's other strategies such as advancing the processes for the concrete, during, for example, pretreatment process of the raw materials, the mixing, the casting, and the curing, as well as the new construction method development, such as using the more lower carbon construction technology, such as 3D printing, such as robotic construction. So this study, I will focus on the advancing the processing through the carbonation sequestration. So the production of the raw materials, such as the cement and some of the fine aggregates, it releases some of the CO2, but this CO2 actually can captured back or sequestered by the concrete materials, generally through or simply through this reaction. I cannot see the pointer, sorry. So through this reaction, the calcium will react with water and the CO2 to generate the calcium carbonate so that it can embed back to the concrete. So in terms of the concrete manufacturing, the CO2 sequestration can take place in 3 stages. So for the pretreatment stages, the raw materials rich with the magnesium or the calcium can be such as the steel slag and the recycled carbon aggregate. It can be cured in a CO2-rich chamber. And then it will react with the CO2 and some of the water to generate some calcium carbonate shells on the surface of the solid wastes, and so that it can improve the properties of the solid waste and for the upcycling into concrete. So for the second stage is the mixing stage, so the CO2 can be injected into the fresh concrete during the wet mixing process. So through this process, the CO2 will react it with the wet cement and generate some of the nano-calcium carbonate particles, which can refine the microstructures of the concrete and improve some of the properties, especially the mechanical properties and durability. And for the curing stage, the concrete can also be cured in a CO2-rich chamber with a controlled environment, normally some of the pressure and the temperature controlled. So during this stage, the nano-calcium carbonate can be precipitated in the pores of the cementitious systems and for refining the microstructures. So compare the 3 kind of methods or pathways. They have different advantages and disadvantages. For the pretreatment methods to pre-treat the raw materials, the good part of it is it can recycle the industrial waste. It can treat the industrial waste. It has relatively high CO2 sequestration rate. However, it is hard for large-scale production because you will need a special kind of reactor, and you have to rotate it to homogenize the raw materials to expose it to CO2 and some of the water. So this is kind of energy intensive. And for the mixing stage, just inject the CO2 into the fresh concrete. The good part of it is it's applicable for casting place construction. But from what's my limited knowledge from the reports, the sequestration, CO2 sequestration rate for it is very low. It's only 0.3%. And also, when you inject it, as the mixer is now like sealed, so there will be like CO2 released back to the environment. And for the curing stage or the CO2 curing methods, the good part of it is it has very high sequestration rate, relatively high, or let's say. However, again, it is hard for the casting place application. So this study, we just propose alternative methods to enable the casting place concrete application with enhanced CO2 sequestration rate. So the methods we use is to bubble the CO2, into a calcium-rich solution, and so that you will generate some of uniform distributed calcium carbonate suspension. So it's very small particle size, and then we add the solution together with the mixing water to the concrete during the concrete mixing, and then we will prepare the specimens. So this process is compatible with the existing industrial facilities and conventional, and it is convenient for large-scale production. So for comparison, we prepared two groups of the calcium carbonate suspension. The first one, we call it CI suspension, as it is prepared by the injection of CO2 to the different concentration of the calcium hydroxide solution. And so we will prepare this kind of particles in this way, injection way. And very important is you have to use the air stone to distribute the CO2 in the reactor. And we also, again, for the comparison, we prepared the CP suspension. So this suspension is prepared with different content of nano-calcium carbonate powders. So as some of the researchers just directly use the nano powders into concrete to enhance some of the properties of the concrete. So just for information, the nano-calcium carbonate properties is shown here. So particle size is in the range of 30 to 60 nanometers. And the calcium carbonate content is greater than 97.5%, is pretty pure kind of nanoparticles, calcium carbonate particles. So in total, we investigated 10 mixtures, two groups. So one is with one group is the mixtures prepared with the CI methods, or we call them CI mixtures, and the other is the mixtures prepared with directly adding the nano calcium carbonate powders. We call it CP mixtures again. So to prepare the CP mixtures, or to prepare the suspension prepared by the nano calcium carbonate powders, we just have to disperse it before we use it, as if it is because if you don't do that, the nanoparticles will agglomerate it, and that will compromise the mechanical properties and the durability. So based on the literatures, we used the ultrasonic bath. We just used to disperse it at 20 kHz for 10 minutes before we use it. So here shows the fresh properties or the mini sound flow when we fix the high range water reducer. So both the CI mixtures and CP mixtures will increase the calcium carbonate concentration, it decrease the mini sound flow. And the CI method just show higher reduction rate than the CP methods. But if you if you look at the compressive strength, the 28 is compressive strength, at the same calcium carbonate concentration, the CI mixtures show significantly higher strengths than directly using the nano calcium carbonate powders. So both of the Ci and the Cp mixtures, when you increase the calcium carbonate concentrations, the hydration, the hydration is accelerated and promoted, and more like hydration products are produced by using of the nano kind of calcium carbonate suspensions. And because of the use of the nanomaterials due to the filler effect, the hydration is promoted and the microstructure is refined, as you can see. Both the Ci mixtures and the Cp mixtures shows reduction in the porosity. And the Ci mixtures was even like 8 to 20% lower than the porosity of the mixtures prepared by the nano calcium carbonate powders. So we think the improvement of the mechanical properties and the better refinement of the microstructure is because the Ci methods can generate more uniform or more finer kind of nanoparticles. So we conducted the testing to test that. As you can see, the calcium carbonate particles in the suspension produced by the Ci method, injection method, have finer particle size and have better dispersion and homogeneity than that produced by the Cp methods. The Cp methods, we just for comparison, we do one with ultrasonication and one without. So with sonication, it improves. It improves the homogeneity and dispersion. But compared with the Ci methods, the particle is coarser, and it's not as well as that one. However, so the upper figure, the data was collected right after we generate such the nano calcium carbonate suspension. But with time, as you can see, the nano particles agglomerated with time. With the retention time, we don't do anything. So it agglomerated with the retention time. So when we produce that, we will have to find a way to stabilize the particles. So that's why we're using the polymers, the polyalkylate acid polymers, to stabilize the calcium carbonate suspension when we just use the Ci methods or Cp methods after we disperse them or create them. So the preliminary study shows that the suspension dispersion level is stable in 3 days when we're using 0.2 to 0.4% polyalkylate acid, but more studies needed here to prolong the stable time. So hopefully I will have some good studies to publish this soon to show you more details about this stabilization. So again, for the SCM observations, we also observed that the Ci mixtures with 2% of calcium carbonates shows like better dispersion, particle dispersion, than the Cp methods. So the Cp methods, even though we have some kind of ultrasonic sonication, still there's a lot of spots we observed the agglomerations. So we also just divided our specimens into like 16 pieces. So each of the piece we test the TGA and to calculate the calcium carbonate content for different the pieces. And you will see that the Cp method shows like bigger variations than the Ci methods, which again proves that the Ci methods leads to a better calcium carbonate dispersion level than the Cp methods. So we also evaluated the life cycle carbon footprints, and some of you may consider, oh, you use the calcium hydroxide, it actually is not like very low carbon. So we consider that. So the calcium hydroxide also absorbed the CO2. So we have to consider the CO2 sequestration of the calcium hydroxide. But overall, this is the data we used for the evaluation for the carbon footprint. And the result shows that the Ci methods reduce the strength normalized carbon emission by up to 15%, which is the reduction rate is 40% higher than the Cp methods that are the same calcium carbonate concentration, which is 2%. So we can also use these methods the injection methods to treat the solid wastes. So the solid waste, what I mean is the porous kind of solid wastes. Here I just shows the example of the OPS specification fly ash, or the OSFA in short. So this materials is really landfilled, and we wanted to just to improve the properties of the solid waste for upcycling. So the same, we just inject the CO2 into the suspension. The suspension have the calcium hydroxide as well as the OSFA particles. So with time, we find that the nano-calcium carbonate is precipitated on the surface of the OSFA, as it has very high surface areas. So it's precipitated on the surface and strengthening the surface of the solid waste. And with time, this kind of surface or this kind of coatings will will be getting thick. So again, with this method, we coat the nano-calcium carbonate on the surface of solid waste, and we compared four different cases. One is without any OPS specification fly ash, the mixture. So here shows the mixture design. And the FA20 represents the system with 20% OSFA without any coating. And the CC-FA20 represents the mixtures with 20% OSFA and with the nano-calcium carbonate powders, just dry powders. And the CC-FA20 represents the mixtures with 20% OSFA coated by the nano-calcium carbonate, by the way the CI method or the injection methods. So this shows the difference. So the CCFA is the nanoparticles distributed in the system, but the CC-FA is the nano-calcium carbonate precipitated on the surface of the OSFA. So here it shows you the 28 days compressive strength. So as expected, when you use the porous solid waste, the OSFA significantly reduce the compressive strength. But when you use the nanomaterials or nano-calcium carbonate, the strength is catching up. But compare with directly adding the nano-calcium carbonate powders, the in situ produced the nano-calcium carbonate powders have the better strength improvement. So again, this is because the injection methods is created more uniformly and finer particles, and that's just give a better promotion for the hydration and the refining the microstructures, as we did the mercury intrusion porosimeter testing results shows that. So the injection methods just shows the lowest results in the porosity. So in the conclusion, we proposed the alternative approach to utilize the CO2 to prepare the low carbon cementitious materials. So this method can have a high CO2 sequestration efficiency and reaction rates, and it can produce uniformly dispersed nano-calcium carbonate powders with low energy consumption, and to give high mechanical properties, and it is available for both cast in place and precast of concrete application. And also through the CO2 injection treatments, the porous waste or solid waste can be coated, which can enhance the mechanical properties of the UHPC incorporated such a materials or such a suspension. So this method is more effective than directly adding nano-calcium carbonate powders into concrete. So this work is conducted by two of my PhD students, Mr. Zhuo Liu and Mr. Jiang Du. And thanks for our sponsors, NSF and US Army. With that, I would like to thank all of you for your attention. I'm not sure if I have time for any questions.